I'm going to deal with the interference of light. This is chapter 22. But I'm talking about the interference of light because we've been talking about interference. But perhaps we should back up a little bit, because how do we even know that light is a wave to begin with? You only get interference between things that are waves. And the nature of light had been heavily debated from time immemorial, all the way back to the ancient Greeks. But early on, there was an idea that light was made out of particles. Now think of the modern idea of a photon, although there's some complications to that. Now the reason for thinking that light traveled as little particles of material was that light travels in straight lines, as far as we could tell. That is, when you've got a light source here, and you have an object and it casts a shadow, there are straight lines you can draw from the source to the edges of your object and down to the edges of the shadow. So light appears to travel in straight lines. We get what's called a geometric shadow that way. That supported the idea that it was particle-like. But, Sir Isaac Newton, in his first really big book, Optics, promotes the idea that light is made out of particles. But, contrary to that, at the same time, the Dutch astronomer and physicist and mathematician and so on, Christian Huygens, it looks like Huygens, but the Dutch pronunciation is closer to Huygens. Actually, it's closest to something like Huygens, and I can't do that gagging sound with the G. Okay. The book discusses Christian Huygens just a little bit later, but I think he's important to bring up now. He lived in the 1600s, again, roughly contemporary with Newton, I think a little bit older. And he promoted the idea of light as a wave. Now, what do waves do? Well, for one thing, waves can bend around obstructions. If you have a wave, let's draw the wave crests. Let's see. Well, let me draw kind of a three-quarter view of ocean waves. There's an island in the ocean. And if I've got waves coming in here, now let me just draw the crests now. When they hit the island, they can bend around it. And that can create interference patterns on the lee side, well, not the lee side, on the down wave side, on the trailing edge, let me put it that way. If it were the wind, the downwind side would be called the lee side, but these are waves. Okay, so they can bend around this like that. So Huygens proposed the same thing could happen with light. That light would travel by, at every point, you have this vibration, and that point becomes the new source of the vibration, and that's how they propagate. And therefore, when light comes to an obstruction, now I'm looking edge on to some, let's say this is a piece of paper with a hole in it. If I have my waves coming in this way, all right, let's make them plane waves so the crests are parallel to each other and they all move in parallel lines straight. When it comes to here then, what happens is that it bends around and every point becomes a new wave source. So it emits a spherical wave, or circular if it's two-dimensional, and we'll get to the mathematical details of that in a few sections. But on the edges here, you see it rounded, and in the middle, it's mostly flattened out, because all of those circular waves or spherical waves kind of line up with each other. and it gets rounder as it gets farther away from this small-sized opening. That little flat spot smooths out. Okay, so the debate between Newton's particle wave nature and Newton's particle nature of light and Huygens' wave nature of light was debated back and forth. But by the 1700s, things seemed to be pretty well settled in favor of the particle nature of light. But there came on some experiments in the late 1700s that confirmed the wave nature. The most famous of these is Young's double slit. Now, Thomas Young was an English physicist, linguist, biologist, botanist, I think, possibly mathematician, physicist, anyway, oh, and medical doctor. He did pretty much everything. My freshman physics professor, Jack Taylor, at Rhodes College, described Thomas Young as the last man who knew everything. At least everything there was that was worth knowing about in a scientific sense. He was a medical doctor, he was a physicist, he was Foreign Secretary of the Royal Society. The Royal Society was and is the premier British scientific organization, which has a royal charter, hence the name. He made one of the first big contributions to decoding, to translating Egyptian hieroglyphs using the Rosetta Stone, a bit before Champollion came on and did the biggest step forward. Thomas Young did about everything. If you've had the first semester of mechanics, you will have covered then Young's elastic modulus for material, which talks about how stretchy or compressible it is. But he also then did this experiment with light waves, showing that they were, in fact, waves. Let's imagine that we have two narrow slits opened in a piece of cardboard. We're looking edge on, piece of paper like that, two little narrow slits cut in it. Now, I've got my light wave coming like this. So it's going to ripple outwards from each one of these here. This is like the two source speakers that I did in the previous lesson. Now let's project this light onto a screen some distance away. Okay. There's the symmetry axis of all of this. Now, we have slit 1 and slit 2. If I've got, get my other chalk here. If I want to know how bright is the light at a given point on the screen, the distances are what's important. So, well, ultimately what's important is, do I get constructive interference, destructive interference, or something in between? So you have, let's say I'm going to go from drawing the wave crests here to the, maybe I should just still draw the wave crests. So I've got crest, I'll just draw the little hatch lines here. And then this one starts off with a crest here. I may not line those up perfectly. But you see, these two distances are different. These two slits, because the way that I've set this up, I have the plane wave coming in perpendicular to the wave is moving this way, exactly perpendicular to the card that has the slits in them. Therefore, the wave, if there's a wave crest here, there's also a wave crest here, which means my two sources have no inherent phase difference. That delta phi naught is 0. When one emits a crest, the other one emits a crest. So the only difference between the wave coming in from this one and the wave coming in from this one is the difference in the length that they travel, the path difference. There. So how do they combine? Well, in this case, notice that I've got this one's wave crest is pretty much lined up with that one's trough. And so you get destructive interference. But if I were in a different place, let's say in the middle, the wave crests line up, and I get constructive interference. In fact, it will always be constructive, exactly in the middle between the two. All right, so let's see what the overall pattern looks like. Actually, I'll tell you what the overall pattern looks like first. You're going to wind up with, let me think, what's the best way of doing this? Here's the screen. I will draw the intensity of the light. Intensity? No, the amplitude. I'll draw the amplitude out this way from the screen so that you can see the function. Actually, maybe I'll draw it over here. So you're going to get a peak in the middle, and it'll go down on either side, like this. There. So we'll have the y-axis be there, and the brightness of the light, the amplitude of the light will be going out this way here. Okay, let's get some math involved on this. The width, the distance from our slit to the screen is going to be a length capital L, and the spacing between the two slits will be a lowercase d for distance. Now, let's go in on the, let's see here. Okay, now the angle that these rays move away from the axis is going to be theta. Now I'm going to mark theta 1 for this one here, and angle theta 2 for that one. And then I'm going to make the origin over here, this will be y equals 0. Okay. So whether you get a bright, what we call a fringe, or a dark black fringe depends on the phase difference between the two. Recall that the phase difference, delta phi, is equal to, in general, 2 pi times the path difference, delta r, divided by the wavelength, lambda. Assuming we have the same wavelength, and we do here, plus the inherent phase difference, delta phi naught. Now, for the double slit, the way that I got this set up, with the light rays coming, the plane wave coming in this way, remember, these are in sync. They have no inherent phase difference. It's just a way that I've set it up. You could do it a different way. Okay, now, let's say that I want to look at constructive interference. That's the positions of the bright fringes. For constructive interference, I know that the phase difference has to be even multiples of pi, 0, 2 pi, 4 pi, 6 pi, and so on. And we've written that out as m, the mode number, times 2 pi. Really a better way of doing that is 2 pi m. Letters come after your numbers usually. There we go. This is constructive interference. There. By choosing that. 2 pi's cancel. Make sure that's all on the screen, on the board, yes. Now, solving for the path difference, that's interesting. Delta R is m times lambda, where m is 0, 1, 2, 3, and so on. Okay, this is the position, this is the path difference needed for constructive interference. Now, what angles do these appear at? Here it gets a little more subtle. You see, the angles are different for these two rays. But we can make the assumption, which is fair enough, that the distance between the two slits is small and that the distance from the slits to the screen is large. So as long as the distance to the screen is much, much larger than the distance between the two slits, these angles will be approximately the same. And so theta 1 is about equal to theta 2 in that case. Okay, so doing that then, I need a little more room from the camera. I'm going to redraw the slit slightly different, slits slightly differently now. Now, there. Okay, so this is R1, that's R2. For L much greater than D, theta 1 is about equal to theta 2, and I'll call both of them theta. So that's theta, and that's theta. But look at this. This is also theta. If I drop from slit number 1 a line perpendicular to ray number 2, there. That is theta. The angle from slit 1 to that line drawn perpendicular to R2. That's a right angle. This distance is D, and you take the sine of angle theta is the opposite divided by the hypotenuse, that's D there. So let's see here. This is delta R. The difference in the path lengths. Just when they get up to the screen here, that's how much farther this one goes than that one. Okay, so delta R, D, and theta. Sine of theta is opposite over hypotenuse. So delta R, which is what I'm really interested in, is D sine theta. Now that turns out to be useful. So I'll put this in over here. D sine theta is that. But what I really want is the angle theta itself. It's inside the sine. Now I could divide by d and take the arc sine, or the inverse sine, but inverse trig functions are not, they're missing. Instead, as long as I'm not wandering too far away from the axis, the equation can be approximated with the small angle approximation. So for small angles less than 1 radian, much less than 1 radian, sine theta is about equal to theta. So d theta is equal to m lambda, and theta then is equal to m times lambda over d. Now I'm going to subscript theta with an m. That means that I'm indexing it, really, with what the mode number is there. We'll call it mode. Okay, where m, again, is 0, 1, 2, 3, and so on. This gives me the angles at which these bright fringes are emitted. Make a note, this is for the bright fringes only. So what positions on the screen are they? I've got the angles. Positions are very easy. Now it's just a matter of trigonometry to get the angles. There's the screen again, the two slits. Oh, sorry, there's the slits there, the two slits. And here's the screen, and there's a length L. And if the y-axis goes up with the origin here, and that's my angle theta. Theta 1 and theta 2 are both theta here. And really I've got two thin little rays going next to each other, but I'll just draw from the center of the slits. Then, that's a right angle, that's the opposite side, that's the adjacent. Tangent of theta is equal to opposite over adjacent, which means it's y over L. Okay. Now, for small angles, theta much less than 1 radian, tangent of theta is about equal to theta. Great. So now I put theta here is equal to y over L. Use what I just learned over here. And that means m lambda over d is equal to y over L. And I can solve for y. Y is equal to m lambda L over d. And we'll subscript y with an m, so we know which one we're dealing with. And m, again, is 0, 1, 2, 3, any integer. Really, again, negative integers work just as well as positive ones, but I'll show you, it's symmetrical anyway. And these are the screen positions, the y-coordinates of the bright fringes. Okay. Now, take a look at one more thing of the intensity of the light. How bright is it? The flux. It's not just the amplitude, remember. Flux is proportional, intensity is proportional, brightness is proportional to the amplitude squared. So let's get that over here. All right, recall that intensity is proportional to amplitude squared. If it's proportional, that means I can write it as some constant, some number, times the amplitude squared. or I use CONST for constant. We don't know what C is, but it turns out we're not even going to care what it is. So, what's the amplitude? All right. If you recall, again, I'm saying recall, because we have had this in the previous chapter. For interference, we have the interference of two ways. The amplitude changes with 2 times the amplitude of either of the waves times the cosine of the phase difference, delta phi, over 2. Now, I'm taking the absolute value of this because you can have it be either way. Positive or negative gives you the same result. And this is equation 21.36. Okay. What's delta theta? The phase difference. Delta phi, I mean. Delta phi is 2 pi times the path difference, delta r, over the wavelength. So what fraction of a wavelength are they different? Times 2 pi. Plus what's called the inherent phase difference, delta phi naught, which gives the difference in their starting. Now, for the double slit, as I have it set up, again, there is no difference in the inherent phase. Inherent phase difference is 0. So we set that to 0. We're left with this. Okay. Now, remember, just a minute ago, I had that the path length difference, delta r, is equal to d sine theta. Theta is the angle that they're emitted from the slits. Okay, so I put that there. We don't like having the trig functions in here. We want something a bit simpler. If we keep the angle away from the axis small, theta much less than 1, then we use a small angle approximation. You're never going to know which kind of version of the small angle approximation I'm going to use. In this case, I'm going to use the fact that sine is about equal to the tangent. Why? Because the tangent is the ratio of opposite to hypotenuse. So opposite to adjacent, opposite over adjacent is the tangent. So, and the tangent is then y over L, so I'll put that right in here. So that's 2 pi times dy over lambda L. Make sure that that's correct. It appears to be. So I just skipped a step. I could have done that in the second step. There it is. All right, that is my phase difference, delta phi. Okay. Now, let's put that back in the amplitude equation. So I've got 2a times the cosine of this over 2. Need to block that off a bit. 2 pi dy over 2 times lambda L. Those cancel. And I'm left with the amplitude being the absolute value of 2a cosine of pi d over lambda L times y. Okay, now I've got to put it in here. Let me get over to the next section of the board again. So the intensity of the interfering waves is equal to some constant of proportionality times the amplitude, total amplitude squared, and the amplitude I just got is this. Let's see, 2AC, 2CA. Wait a second. Oh, I'm going to square that, so it's 4CA squared, yeah, times the cosine squared of pi d over lambda L all times y. Notice that I don't have to put the absolute value symbol now because the cosine squared is going to be positive, or 0. Okay, there's my intensity. But I can do one better. If you recall, well, if we had two waves that weren't interfering, just two sources with no interference, well, let me say, a single source, I put I1 for one source. It's proportional to its amplitude squared, so in this case it would be equal to CA squared. Single source intensity. Well, that means I can write the total intensity as 4 times a single slit intensity times cosine squared of all that. Okay, now what is the maximum intensity of these white fringes? Take a look here. What's the maximum value of the cosine? Is 1. So cosine squared, the maximum value is also 1. And therefore, the max intensity is 4 times the intensity from a single source. Which is interesting. It's not 2 times that, it's 4. So interference gives us this interesting and somewhat surprising result. Okay, so what do these look like then in practice? Now, I don't have a projector screen in here, unfortunately. You really need that in order to do this with the light. But I'm going to do my best with a piece of white paper. Okay, now wipe my hands off, get chalk up on them. Let's see. I can take this paper and clip it . Yeah, that'll do. I'll clip it up here. All right, we'll see how well that goes. Probably going to want to hold this. Bring it up closer to the camera. Let's see. I'll turn the lights off. Now, I've got here a laser pointer. It's got both red and green lights on it, green and red lasers. It's not just a light. And this is a card that has some metal foil with slits cut in it. You can get more precise edges with the metal slits than with the paper. zoom in slightly. Okay. So let me shine this through here. There. Not sure how well you can see that on the camera, but I've got a bright central maximum within the interference pattern, making the ripples off to either side. Now, if I space the lines farther apart, I've got a different spacing then of the, if the slits are farther apart, then the spacings of the fringes are actually, let me see, closer together. There we go. A little farther apart, a little closer together there. Now, the wavelength of light also matters. That'll pin it pretty well. So the wavelength of light matters as well. Y, for the positions of the bright fringes, y sub m, y coordinates equals m lambda L, the distance to the screen, divided by d. So for a given spacing of the separation of the slits, the longer the wavelength, the farther apart they're going to be spaced. So if I take green, which is a shorter wavelength of light, I get that spacing there. Now let's see. There we go. And for the same slit, the red laser gives me that, and you can just see the spacing being wider. Fortunately, these don't aim the same way. They're a bit narrow. Okay. Another interesting thing is that you can get a pattern off of a single edge. And you will get not interference, but diffraction. And if you have a single slit, you can also get this what's called diffraction as well. They're making a streak off of the edge of the whole card. But for that, we've got to get into the next section. All right, oh, one other thing. The slit, the direction of the slits matters. The fringes, there are some good fringes. The fringes will be in a line that is perpendicular to the direction of the slits. So if I have the slits horizontal, my fringes are vertical. If the slits are vertical, the fringes are horizontal. They always make a perpendicular, or are arranged perpendicularly. There we go. Y slits. Okay, and here's the end of this lesson.